Welcome back to the series on statistics. This video is going to be a little bit dry, quite frankly, just like the last one. The problem with statistics is that it sounds really boring, and then the first couple topics within statistics, you have to cover basic probability and you have to cover foundational ideas to statistics, and these generally are not very complicated ideas. So I ask that you try to bear with me through this second video here, and I'm going to get all of this boring nitty-gritty stuff out of the way, and in the next video I'll talk about the binomial distribution, which is where statistics starts to get really interesting, and then everything after that should be good. I'm going to try to make this as interesting as possible, but if you feel like it's a little bit dry, just throw the video on ×2 speed. I watch all my math videos and science videos on ×2 speed unless I feel like I need to slow down. Makes them a lot more entertaining and just interesting to watch, and I can watch a lot more of them. So I always recommend that. But with that being said, let's get started. The first topic in this video, we need to talk about the difference between a statistic and a parameter. So parameters are numbers, proportions that make statements about populations. So every 10 years in the United States, this is the most popular example, there's a census conducted. And a census, in theory, they go out and they actually survey every single citizen of the United States, asking every single one of them certain questions, and this all gets published in this enormous compendium of data that's available for everybody. There's a reason that this is done every 10 years. There's about 350 million Americans, so it's very difficult to actually go out and conduct this research. But these statements that are within this census data are not estimates. They are precise statements about the parameters of the population. They are the parameters of the population. For example, if in the census it says that 51% of Americans are women, that is a precise statement. It is not an estimate. Now, this is a very challenging task. You can imagine it might get easier as your populations get smaller. For instance, if you're trying to make statements about the populations of students at a university, that'd be easier than making statements about the population of the United States, or citizens of the United States. But it would still be very challenging, and a lot of times in the fields of research, you do not want to spend all your time conducting gathering the data. You want to spend your time doing the analysis of the data that you gather. And so that is where statistics comes in. Statistics allows us to take samples. Instead of surveying every single student at a university, you might only survey 30. But what statistics is the science of making definite, precise, accurate, true mathematical statements about the parameters of a population based on the statistics that you gather of a sample from that population. And so the art of statistics deals with not just the application of this process, the analysis of the sample data and what that tells you about the population, but also the art of sampling itself. How do we conduct our samples to where it gives us the most accurate information about the population? You can imagine that this is going to be very useful in every single field, from business to politics to science and mathematics. And you could even imagine situations where it's impossible to do a census, so to speak. For example, if you're an ecologist and you're trying to make statements about the water quality, your population is going to be the water that you're dealing with within some reservoir. It might be an ocean, for example, and you can imagine it is not going to be possible to take all of the water in a lake or a pond, remove it from its environment, put it through some sort of data analysis machine, whatever ecologists use, I'm not sure, and then put it back where you got it. That's just insane. And so what you would do is you would take several different samples from the water, and statistics would tell you that you might want to take samples from different places in that body of water. You might want different amounts in each of your samples. But basically what you're doing is you take these samples and you take measurements and you take data based on those samples, and then based on those measurements, based on that data of your sample of the population, you will be able to make precise mathematical statements about the parameters of the true population, or the true parameters of the entire population. And so that's what we're going to learn how to do. That's the science that we're dealing with here. And let's get started with a discussion of a couple basic parameters that you might be interested in. So one thing you might be interested in when you're dealing with sets of data is averages. There's different ways that you could imagine an average, and one of those ways would be the classical approach where you sum up all the elements in a set and you divide by how many elements there are, and that should give you the average. So what that is in statistics is we call it the mean. So here I have two different sets. One of these, denoted with the S, is going to be a sample. And so let's just imagine that this is a sample of test scores from students, maybe in like an introductory calculus class with like 300 students or something. So instead of asking every single student what they got in the midterm, let's just imagine that this is a sample of 7 students. Now here on the right, I have denoted with the P a population. So let's imagine this is a graduate class that only has 7 students, and these are the scores that they got on the test. 6 students, sorry. And so if we want to compute the mean here, what we're going to have to do is sum up all of the elements in the set. And so I'll denote that by all the elements in the set. We're going to add them all up, and then we're going to divide by how many elements there are. And so with a sample, that's going to be denoted 1 over n, where n is your sample size. Sloppy, but you get the idea. Very, very important here. We are denoting the mean here with this symbol, x bar. That's because we're talking about a sample. The analog here for a population, we're going to denote the mean with the Greek symbol mu. And so here we're going to compute this exactly the same way. We're going to divide by, instead of the sample size here, we're dividing by the population size, but we're still going to do the same procedure. We're going to add up over all of the elements in the population, and then we're going to divide by how many elements there are. So this is going to give us our mean. Now, if you actually carry out the calculations here, what you'll get is that x bar, our mean of this sample data here, will be 81.143, about 81.143. And our mean of the population data here, this graduate students, the mean score is going to be a 78.17, roughly. And so what does this tell us? This tells us the average score, the mean of this data, is going to be this number right here. And that should make sense. It seems to be that that is about where the middle of both of these data sets lies. But there's different ways that you might think about the middle. One of the more obvious ways to think about the middle would be, well, we've ordered this set from low scores to high scores. We know what the lowest score and the highest score is just immediately by looking at it. What about just the middle value? And so in this case, that middle value would be 81, and this is called the median. And we'll denote that MED. This is going to be 81. And here, for our graduate students, we have 2 values in the middle. There's an even number of elements in this population, and so if you want to compute the median in this type of situation, we need to add these 2 up, or take the average of these 2, for example. So we would add up an 80 and 81, and we divide by 2, and we would get the median is 80.5. Now, what you'll notice is that these are not exactly equal values. For example, here the median is just a little bit less, just a hair less than the mean for our sample data. And the median here is a little bit more for our mean of the population data for these graduate students. And so what does that tell us? That tells us that in this situation, here on the right, it seems like there is a higher score, perhaps, that's pulling that, a lower score here that might be pulling this mean down versus the geometric middle of the data, which is just going to be right in the middle of however it's ordered. And here you can see that 64, that's probably bringing this average down, because 64 is a lot less than 80.5, then 89 is greater than 80.5. That makes sense. Moving over to our sample data here, you can see that the mean is just a little bit bigger than the median, and so what that tells us is that there might be a score that's a little bit higher, perhaps bringing that mean up just a little bit from the geometric middle of the data. And here we see that 95 there. That could be the culprit. However, just as a general statement, these means are in both of these situations, they're not that different from the median. And so this is getting very, very, very peculiar with our picking of the data. It does seem that the data is pretty symmetrical here. And by symmetrical, we mean that there's roughly the same amount of data to the right of the mean as there is to the left of the mean in both of these situations. And so we don't really have some sort of outlier or anything like that. And so I've made the statement here that the median is going to be the geometric middle of our data. Just to be a little bit more clear and specific about what that means is that when you take your data and you order it in ascending order, the lowest value on the left end of your data and the highest value on the right, the middle of that data is going to be your median. So here in this case, we have 81 is in the middle. If you were to eliminate these things like you probably did in grade school, you would be left with 81 in the middle. And then here we're taking the average. But the precise definition of what that median is that in an ordered set of your sample or your population data, the median is the value with which 50% of your sample data or your population data lies beneath and 50% lies above. So it's the 50th percentile, so to speak. And here the math doesn't work out quite right because we're dealing with 7 data points. And so it's just an odd number. It's a very small number. So 3 out of 7 is not quite 50%, but it's as close as you can get with only 7 data points. Here, on the other hand, because we have an even number of data points, there's 6 here, and we had to take the average to compute the median of 80.5 here. What you'll notice is that these data points to the left of the mean, so to speak, this 80.5, they're all less. So 50%, 3 out of 6 of these data points are going to be less than the median, and 3 out of 6 of these data points are going to be greater than the median. So this precisely does encapsulate the 50th percentile of the data, or 50% of your data lies beneath and 50% of your data lies above the median. So that's exactly what the median is, as opposed to a raw numerical average of your data, which is what is given by the mean. So just to introduce a little bit more vocabulary here, quartiles and percentiles. We have that if X is the 97th percentile of a data set, for example, then what that means is that 97% of the data in that data set is going to be less than that X data point. So 97% of that data will be less than X if X is that 97th percentile. By definition, then, this means that the median is the same thing as the 50th percentile of the data set, just like as we saw in this example with the population, where 50% of the data lies below this median. And a quartile tells us increments of 25%. So, for example, the first quartile here is going to tell us the 25th percentile of a data set, or that data point where 25% of the data in the data set lies below that point. The second quartile will tell you the 50th percentile of the data set. That's just equal to the median. And the third quartile will tell you the 75th percentile, wherein 75% of the data will lie below that third quartile, or Q3. Now, moving on here from our conversation about the center of a data and these percentiles, we want to talk about the spread of a data. How different is most of the data in our data set from whatever our measures of our center are, what our mean or median. And in order to talk about the spread of the data, we need to talk about variance and standard deviation. And these are our standard measures and statistics that tell us how widely variable our data set is. Is it well behaved? Is most of the data clustered around some centered point? Or are there just wild undulations in our data? So how could we go about doing this? Now, for the moment being, I'm actually going to get rid of this sample data because standard deviation for a sample is actually calculated just a hair bit differently than standard deviation in theory, as you would calculate it for a population. It's so similar that it's not even worth talking about in this video, and I'm just going to talk about that slight difference whenever we talk about sampling. But for now, if we want to talk about standard deviation, we want to get some idea of a measure of how different the data in this data set is from its average. One thing that immediately might jump to mind is you could just take the sum over all of the elements in this population, and you could just take the difference between each of these elements and the average of the population, or the mean, and you could sum up all of these differences, and then you could divide by how many elements are in the set, and this would give us our standard deviation. right? This would give us a good spread, or a good idea of how spread out our data is. Could you see a problem that might emerge if you use this formula? I encourage you to pause and think about it. This symbol here, this lowercase sigma, represents our standard deviations, but I do encourage you to pause and think about why this might be a bad method here. Right, so hopefully you've paused the video and thought about it, maybe tried to carry out this calculation, this summation here. And what you might have noticed if you did try to carry out this summation is that here on the left side, I believe our mean for this population was about 78, something like that. On the left side, when you take the difference between these data points and our mean, you have 64 minus 78, 72 minus 78. These are all going to be negative values. And then here, as you move towards the rightmost side of this data set, the difference between these data points and the mean, 83 and 78, 89 and 78, these are going to be positive values. And so in summing all of these differences up, really what you're doing is you're not measuring the spread at all, or you're not measuring the difference between each of these data points and the mean here, because these negative differences, these values in our data set that are in our data set but they're less than the mean, are getting, those differences are getting canceled out by the values in our data set which are greater than the mean. And so the way that mathematicians and statisticians came up with to keep track of the magnitude of these differences without canceling these differences out, these negative and positive differences, because really what we want is just a measure of how spread out the data is, how different each value in this data set is roughly from the average, is that they just squared this quantity here. They squared this quantity. Because then it doesn't matter if you're dealing with a negative value or a positive number. Either way, when you square it, it will be a positive number. And then when you sum up all of these elements, that will give you a measure of spread for your data. But this isn't really what we want when we're talking about a standard deviation from the mean. Something that will tell us you would imagine the standard difference that each element is from the mean. That's what we originally wanted, and we had to throw in this square here in order to actually compute something meaningful. And so we call this idea here, we call this the variance. And it's just a scalar quantity that tells us what the spread of the data is in general. It's some quantity related to the spread of the data. But if we want what we were originally after, we can get a better estimate for it by taking the square root of this quantity, because then this just becomes some sort of method of keeping track of the magnitude of differences without canceling negative and positive differences out. And then when we take the square root of this, we kind of get what we originally wanted, which was a measure of about how different each element is from the mean. And so the square root of this entire expression here gives us our standard deviation, which you can imagine is denoted by just this lowercase sigma. And that's why the square root here, or that's why this variance here is notated by sigma squared, is because that's just the standard deviation squared. And if you actually carry out this operation here, what you will find is, I'm going to get rid of this for now just so it's not confusing, is that the variance for this data set, the variance here, is going to be roughly equal to, it's like 65.17, and that tells us that the standard deviation of this data set is going to be roughly equal to about 8.07. Right, so moving on here, what we want to do is we want to incorporate probability into this idea of mean and variance and standard deviation. We want to incorporate these ideas together. So I have a little question here. It says, on a 10-question quiz, every student in a Math 152 course scored between a 60 and a 100. Math 152 at my university, I think, is Calculus 2 or something. But it's irrelevant. Suppose you chose a student from the class at random. What score would you expect them to have? And here we have a little bit of data stored in this table here. Now, important note here, we're told in the question that every student in the course scored between a 60 and a 100. And so it's every student scored between 60 and 100. So these probabilities have to add together to be 1, because every single student is found in this range of scores. So these probabilities should add together to 1. And if you check on a calculator, they do indeed. And also, we're told that this is a 10-question quiz, so there's no such thing as a 95 on this quiz. There's a 60, a 70, an 80, a 90, 100, and those are the only possibilities. So this is what we would call a discrete data set. There's only 5 possibilities here, and every single person, their score is going to be among those 5 possibilities. This is a discrete data set as opposed to a continuous data set. And so if you wanted to find out what the expected score is, or the mean of this sort of distribution that takes in mind both the grade and the probability of the student achieving this grade, we'd have to think about this a little bit differently, because we can't just take the average of the grades, right? Because clearly more students scored an 80 than students that scored 100. And so weighing that 100 equally as the 80 is just not going to give us an accurate picture of what the average score in the class was. And so the way that we deal with this in statistics is that we take a weighted average, where we take the sum across all the elements. Here I'm going to say in the population again, because let's just assume that this is the data for all of the students in the class. So you take the sum of all of the elements in the population, and you take that score and you multiply by the probability. You take the score and you multiply by the probability of getting that score. And you're going to add all of these up. So you take a 60 and you multiply by the 5% chance that you would get a 60. You take the 70 and you multiply by the 30% chance that you would get the 70. And you do this for every single element in this list. And what this is going to give us is the expected value of your score, which here I'm just denoting the score as x. And the expected value here is going to be equal to the mean for this data set. That expected value, you can imagine, is the same thing as the average. If you took a random student from the course, you took a random sample and you pulled one student from the course, and there was a gun to your head and you were forced to guess what their score was, you would imagine that you would guess the average score of the class. And so this average is the same thing as the expected value, and the way that we compute it is with this weighted average when we're given probabilities as well as data such as grade, or sort of, it could be anything else. It could be weights of different items on an assembly line, for example. It could be anything. Here it's grades. So let's compute what the mean of this data set is. And so if you carry out this operation here, we're going to sum across all of the elements in this population, which could be all of these scores here. We're going to sum the scores multiplied by the probability of getting that score, and that's denoted by this p of x here. And so carrying that out, we'll have that our mean, or our expected value for our grade, which is denoted by x, is going to equal, let's see, we have 60 times the probability of getting a 60, about 5%, plus 70 times the probability of getting a 70, 30%, given by our table up here, plus a score of an 80, 0.5, plus a 90 times 0.14, plus 100 times 0.01. And if you add all of these up, you will get 77.6. And you could imagine that this seems pretty reasonable. I mean, if you look on this data set, there's clearly more scores that fall below an 80. Even though most of the scores are an 80, there's about 35% of the scores below that and 15% above it. So you would imagine that the average would be pretty close to 80, but a little bit less. And that's exactly what we find. We find that it's 77.6. So this makes sense. This is how you would compute that average. Now, how would you deal with the standard deviation in this situation? It's a little bit more complicated here now that we aren't dealing with just the standard deviation of a one variation data set. We're dealing with that, but we have to take in mind the probability of each outcome in addition to the outcome itself. So I encourage you to pause the video and think about that. So hopefully you gave that a shot. The way that we're going to compute this is actually in a manner that is not very different from the way that we computed the mean. We're going to sum up across all of the elements in the population here. This is a population, not a sample. And we're going to sum up the difference between that data point and the mean squared, just like we did before, but we're going to multiply by the probability of that event happening. And this is going to tell us our variance. So it's a lot similar. It's very similar to the equation we saw before for variance. This is just how you would deal with that, taking in mind those probabilities of each outcome. You take the deviation of each outcome, the difference between that outcome and the mean, you square it to keep a track of the magnitude of the difference, and then you multiply by the probability of that outcome happening. And that's going to give you the variance, and if you wanted the standard deviation, you would just take the square root of that. So just to give you a hint as to how you would compute this, I'm not going to do the entire operation by hand, but you would do 60, that first data point, minus the mean, which we just calculated to be 77.6. You'd square that and multiply by 0.05, and then you would add, let's see, you would do 70 minus 77.6 squared times 0.3. It seems there's a 30% chance of that outcome. And you would just do this for each element in this data set. And if you add all of those up, you'll get a variance of, it looks like 62.24. And what that tells us is that we would have a standard deviation here. A standard deviation, oh my god, it's so bad. It's better. A standard deviation here of 7.89. 7.89. So that is how you can compute the mean here and the standard deviation. Just one final bit of vocabulary here before we move on to the last section of the video, which shouldn't take more than 2 minutes. It's just going to be a little bit about data visualization. This mean, in other statistics textbooks, you might hear the mean described as the first moment of a data set. And if you would hear the mean characterized as the first moment, that might bring a question to your mind, which is what would be the second moment, what would be the third moment. And all those things is instead of the expected value of x, the second moment, for example, the second moment here would be the expected value of x squared, which is computed in the exact same way as the expected value of x. It's going to be the sum, but instead of x here, we're doing x squared. That's exactly the same thing. If you want to compute the third moment, you would do x to the power of 3, and you would do x to the power of 3 there. And so you might wonder why I'm even bringing this up in the first place. The reason that we want to talk about different moments here is because the second moment here is actually pretty useful. It gives us a shortcut to calculating the variance. You can imagine here, I didn't even take the time to write out all of this stuff because it's just such a long calculation. But just some food for thought here. If we want to know what the variance is, we just determined that that is the sum across all the elements in a population of the difference between each element and the mean squared multiplied by that probability of that event occurring. This is the same thing as the expected value of x minus the mean here squared. That's exactly the same thing. You can see this is kind of how we're computing this e of function here, is we're just sticking whatever the input is here, whether it's x, whether it's x squared for the second moment, and we're plugging it into this sum across all the elements in this distribution, and we're multiplying each of those by the probability of that outcome occurring. And so that's kind of what this means. But I digress. If you take this, we can break this up and we can actually distribute the square. So this would be the sum across all the elements in the population. And here we would get x squared minus 2 mu x here. And then we would get plus mu squared. Mu is the expected value or the mean. All of this is going to be multiplied by the probability of x. And then we could distribute this probability of x, and we could break up these terms. So the way I'm going to do that is I'm going to say this is equal to the sum across all the elements in the population of x squared times the probability of x plus the sum across all the elements in the population of, here it looks like minus 2 mu x times the probability of x. And then here we have plus the sum across all the elements in the population of mu squared times the probability of x. And so let's kind of contend with each of these. So here we have the sum across all the elements in the population of x squared times the probability of x. We just determined that this is equal to the second moment, or the expected value of x squared here. That's exactly what this expression evaluates to. And then here, what's going on here? Well, here we have negative 2 mu. Mu is a constant. We determined what it was, actually. We determined it was 77.6. So this isn't going to affect the value of the sum. We might as well pull it out. So this is going to be negative 2 mu, which is the constant, multiplied by the sum across all the elements in the population of x multiplied by the probability of x. Well, that's just equal to negative 2 mu times, well, what's the sum across all the elements in the population of that element multiplied by the probability of that element occurring? That's the same as the expected value of x. Or, another way to put that is the mean. The expected value and the mean are the exact same thing. So this is going to be negative 2 mu times mu. And then what's going on here? We already determined that this mu here is a constant, so we might as well pull it out of the summation. Take this as exactly the same thing as mu squared multiplied by the sum across all the elements of the population of the probability of each element occurring. But if you take the sum of all of the elements in a population of the probability of each element occurring, you'll just be left with 1, because that's the total sum of all of the different possible, the probabilities of each of the possible outcomes that has to add up to 100% or 1. And so this is just going to be mu squared times 1, which is just mu squared. And so what do we notice here is that this is going to reduce to the expected value of x squared, or the second moment. And then here we're going to get minus 2 mu squared plus mu squared. So this is just going to be minus mu squared. And so this is equal to the expected value of x squared, or the second moment, minus the expected value of x, or the first moment squared. And so this oftentimes, very frequently, is a lot easier to calculate. A lot easier to calculate than this original formula here. This sum across all of the elements in P, or in that population, of the difference between those squared multiplied by the probability of that outcome occurring. This formula is oftentimes very much easier to calculate. And so I thought I would include that here. That's going to conclude this discussion on variance and standard deviation in this video. We're going to go a little bit deeper into this when we talk about samples, because we need to talk about how to calculate standard deviation and variance for statistics or samples as opposed to populations. But the general idea is almost identical. There's just some very, very slight changes that kind of take into account the fact that you're not dealing with the entire population, you're dealing with just a subset of the population. The very last thing I want to touch on in this video, just because it's important to understanding basic statistical topics, is we need to understand how these data sets are generally viewed. So there's a couple of different things that you may or may not be familiar with. Here I created a data set, which is just some imaginary set of scores, quite similar to the ones that we talked about earlier. And I plugged them into R to create both a box and whisker chart, or box plot, box and whisker plot. That's going to be this one right here, and a histogram. These are two very common graphs that show up in statistics a lot. And what do these graphs actually tell us? So here, this is the statistics that were given to me from R that tell us the minimum of the data set, the maximum of the data set, the first quartile, the third quartile, the median, and the numerical average, or the mean. And so all of this information, with the exception of the mean, actually, is represented in both of these graphs. Although it's a little bit more obvious in this graph, a couple things. So first off, the way that a box and whisker plot works is that the end of these whiskers here, so like this line and this line, this represents the maximum score and the minimum score. So here you can see the max, we had 94. It seems pretty clear that that's right at about 94. And then here the minimum is that 47 there. And so the difference, or the length of this entire line here, the length of this entire line tells us the range of data that we're dealing with. quite similarly, the box itself is going to tell you something called the interquartile range, which is the third quartile. That's this line right here. It tells you the third quartile minus the first quartile, this line right here. And you can imagine that if the third quartile tells you the 75th percentile and the first quartile tells you the 25th percentile, then the difference between the third and first quartile will tell you where the center 50% of the data lies. And that's exactly what is represented by this box here. So this tells you where 50% of the data lies, and the entire length of the line tells you where 100% of the data lies. And so you can tell from this box plot that 50% of the data is clustered in this region right here amongst the entire set of data, which is clustered along the line. And the last little detail here is that the line, the actual line in the middle of this, tells you the median, that 76 value here is going to be given by this line. Moving on to the histogram, this is a little bit different way of representing the same data. So I use the exact same data for both of these. The box plot is better for when you want to make immediate, quick judgments about where the mean is, or where the median is, where that interquartile range is, how spread out the data is in that way. And the histogram is better when you are wanting to see the shape of a distribution. So on the histogram, you have an x-axis here that tells you the scores. Right, you have one student that scored between a 40 and a 50, one that scored between a 50 and a 60. We had 4 students here that scored between a 60 and a 70. That's what we mean by frequency in this case. This is the number of observances of scores that occurred in each of these categories. So from 70 to 80, you had 70 students, or 7 students score in that category. That's what's represented here, and the reason this is a good representation of the data is because it tells you a sense of the shape. So you can see here that most students scored around the 70 to 80 range. It seems to be clustered around that as the center. And there seem to be a couple very, very, very low scores that are bringing this average down. And so that's something that you could kind of tell from this graph that you couldn't maybe tell from this graph, except for the fact that this line is a little bit longer than this one. It's just not as immediately obvious. And so what you would expect is that these very, very low scores here would be bringing down the numerical average, or the mean, from the median, which seems to be clustered, which would be closer to the actual, what you would call the visual center of this graph. And exactly what you would expect, the median here is 76, and the mean is a little bit lower than that, probably being brought down by this horrible score of a 47 here. And so the histogram here is going to give you a better indication of the shape of a distribution, the way that the data is spread out, whereas this box and whisker plot is a good way of making very quick judgments about median, about interquartile range, where that 50% of the data is sitting, and the range of the data itself. I have one last example in this video, and the reason I chose this is because this deals with a phenomenon that's very, very common in statistics that might take some getting used to. This example says that 17% of victims of financial fraud know the perpetrator of the fraud personally, and we're asked to use the formula to construct the probability distribution for the number X of people in a random sample of 5 victims of financial fraud who did know the perpetrator personally. And we can ignore the rest of this problem. We do not have the tools in our toolkit to solve this yet. That's going to be the subject of the next video when we talk about the binomial distribution. But we're given the fact that 17% of victims of financial fraud know the perpetrator personally, and we're asked to construct the probability distribution for a random sample of 5 victims of financial fraud. And we're asked to see what's the probability distribution for the number of those 5 victims in our sample who knew the perpetrator. And so I went ahead and constructed this using what we're going to learn in the next video in the topic, the binomial distribution. This is a graph that tells you the relationship of victims of financial fraud to the perpetrator. And here, the important part here is that we have probability on the y-axis here, not raw frequency or number of occurrences. Here we're dealing with the probability of each outcome. And so if you took a random sample of 5 victims, there are only 5 possible outcomes. There's a possibility that none of those 5 victims knew the perpetrator of the fraud personally. There's a possibility that one of them did. There's the possibility that 2 of them did, there's the probability that 3 of them did, and the possibility that 4 of them did, and the possibility that all of them did. And there's no other possibilities. There's not the possibility that 6 victims out of 5 victims knew the perpetrator of the fraud personally. There's only the possibilities that exist on this graph. So if you add up the height of all of these vertical bars, you should get 1, because this tells you the probability of each of these occurrences. And if you're interested in how to compute that, just watch the next video. I'm going to dive into that very deeply. But here, what does this tell us? This tells you that if you took a random sample of 5 victims of financial fraud, there's roughly a 40% chance here, a 0.4 probability, that none of them will know the victim. There's about a 40% chance as well that one of them would know the perpetrator. I meant to say perpetrator here. And there looks like to be a little bit less than a 20% chance that 2 of them knew the perpetrator. And here it gets very, very slim. And by the time you get to all of them knowing the perpetrator, the bar isn't even visible on the graph. And so here, this is a way of determining probabilities of certain outcomes visually, graphically. We're going to see this come up a lot when we talk about probability distributions. Very frequently, this is what we want to model in statistics. We want to model graphically the probability of different outcomes. We want to show visually how likely each possible outcome in a given scenario is to occur. And so that's what we've done here. Just kind of get used to that, but we're going to start computing these things and creating these types of graphs in the next video. So I hope that sounds a little bit interesting. To me, it's super cool to see, well, what's the probability that none of these victims knew the perpetrator? We can actually compute that, and we know exactly what the probability of that is. I think that's pretty cool. Hopefully you will too. But this kind of gets all that foundational stuff out of the way. We should be ready to move on to the good stuff in the next video and for the remainder of the series.